Ever wondered why the universe seems so perfectly designed for life? The fine-tuned universe hypothesis suggests that the constants of nature, things like the charge of an electron or the gravitational constant, are exactly what they need to be for life to exist. If these values were even slightly different, life as we know it wouldn't be possible. Take gravity, for example. If the gravitational constant were just a bit stronger, stars would burn out too quickly for life to develop. If it were weaker, stars might never form in the first place. So why do these constants have such precise values? Some scientists think it might not be as mysterious as it seems. Lawrence Krauss, for instance, suggests that what looks like fine-tuning might just be a result of our current lack of understanding. As we uncover more about fundamental physics, these constants might not seem so special after all. However, other theories step outside our universe entirely. Imagine a multiverse, a collection of universes, each with different physical constants. In this scenario, most universes wouldn't support life. Ours just happens to be one of the lucky ones. This idea aligns with the anthropic principle. We observe the universe as finely tuned simply because if it weren't, we wouldn't be here to observe it. And then there's survivorship bias. We exist in a universe that supports life, so we naturally wonder why it's so perfect for us. Still, the more we learn about the universe, the more questions arise. Physicist Paul Davies said, "There is now broad agreement among physicists and cosmologists that the universe is in several respects fine-tuned for life. But the conclusion is not so much that the universe is fine-tuned for life. Rather, it is fine-tuned for the building blocks and environments that life requires." This observation leads us into the philosophical implications of fine-tuning. Imagine a universe where the constants of nature were even slightly different. Stephen Hawking noted that the laws of science as we know them at present contain many fundamental numbers, like the size of the electric charge of the electron and the ratio of the masses of the proton and the electron. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. For instance, if the strong nuclear force were just 2% stronger, hydrogen would fuse into diprotons instead of deuterium and helium, drastically altering the physics of stars and possibly precluding life as we know it. However, not all scientists agree. The diproton argument is disputed by some physicists, who calculate that as long as the increase in strength is less than 50%, stellar fusion could still occur despite the existence of stable diprotons. This highlights the complexity and ongoing debate within the scientific community about how finely tuned our universe really is. Among those who find the fine-tuning evidence persuasive, a variety of natural explanations have been proposed. One such explanation is the existence of multiple universes, introducing a survivorship bias under the anthropic principle. We exist in a universe that supports life because naturally universes that don't support life aren't observed by anyone. But there's more to consider. Davies also pointed out that anthropic reasoning fails to distinguish between minimally biophilic universes in which life is permitted but only marginally possible, and optimally biophilic universes in which life flourishes because biogenesis occurs frequently. This raises the question, is our universe merely allowing life to exist, or is it optimized for life to thrive? The precise formulation of the fine-tuning idea is challenging due to our incomplete understanding of the fundamental constants. The standard model of particle physics has 25 freely adjustable parameters, and general relativity adds another, the cosmological constant, which is known to be non-zero but profoundly small in value. Without a unified theory of quantum gravity, it's difficult to determine the true number of independent physical constants. Some candidate theories suggest the number of independent physical constants could be as small as 1. For example, the cosmological constant might be derivable from other constants. According to one calculation, the small value of the cosmological constant is telling us that a remarkably precise and totally unexpected relation exists among all the parameters of the standard model of particle physics, the bare cosmological constant and unknown physics. In 1913, the chemist Lawrence Joseph Henderson wrote The Fitness of the Environment, one of the first books to explore fine-tuning in the universe. Henderson discusses the importance of water and the environment to living things, pointing out that life as it exists on Earth depends entirely on Earth's very specific environmental conditions, especially the prevalence and properties of water. Fast forward to 1961, physicist Robert H. Dicke claimed that certain forces in physics, such as gravity and electromagnetism, must be perfectly fine-tuned for life to exist in the universe. This idea was further expanded by Fred Hoyle in his 1983 book, The Intelligent Universe. Hoyle wrote, "The list of anthropic properties, apparent accidents of a non-biological nature without which carbon-based and hence human life could not exist, is large and impressive." Belief in the fine-tuned universe led to the expectation that the Large Hadron Collider would produce evidence of physics beyond the standard model, such as supersymmetry. However, by 2012, it had not produced evidence for supersymmetry at the energy scales it was able to probe. Astrophysicist Martin Rees formulates the fine-tuning of the universe in terms of six-dimensionless physical constants. N, the ratio of the electromagnetic force to the gravitational force between a pair of protons, is approximately 10 circumflex 36. According to Rees, if it was significantly smaller, only a small and short-lived universe could exist. If it were large enough, they would repel them so violently that larger atoms would never be generated. Epsilon, a measure of the nuclear efficiency of fusion from hydrogen to helium, is 0.007. When four nucleons fuse into helium, 0.007, 0.7% of their mass, is converted to energy. If epsilon was 0.006, a proton could not bond to a neutron, and only hydrogen could exist, making complex chemistry impossible. Conversely, if epsilon were above 0.008, no hydrogen would exist, as all hydrogen would have been fused shortly after the Big Bang. Omega, commonly known as the density parameter, is the relative importance of gravity and expansion energy in the universe. It is the ratio of the mass density of the universe to the critical density and is approximately 1. If gravity were too strong, compared with dark energy and the initial cosmic expansion rate, the universe would have collapsed before life could have evolved. If gravity were too weak, no stars would have formed. Lambda, commonly known as the cosmological constant, describes the ratio of the density of dark energy to the critical energy density of the universe. In terms of Planck units, lambda is on the order of 10 circumflex 122. This is so small that it has no significant effect on cosmic structures that are smaller than 1 billion light-years across. A slightly larger value of the cosmological constant would have caused space to expand rapidly enough that stars and other astronomical structures would not be able to form. Q, the ratio of the gravitational energy required to pull a large galaxy apart, to the energy equivalent of its mass, is around 10 circumflex 5. If it is too small, no stars can form. If it is too large, no stars can survive because the universe is too violent.